دكتور هل في إمكانية إنك تعطينا إكسترا كويز الأسبوع الجاي؟ ما عليك أمر.
ما I need to finish grading before the final exam. If I give you one next week, you'll be able to do that. طيب بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Welcome to 801. So today's lecture will be the 27th. And in today's lecture, before we start with a few announcements, so homework course posted, and it's inshallah due Sunday, 8th August. Quiz 5 will be this Wednesday. The coverage will be 8.12 to 8.4. So what we did last time in the last time in the class before last lecture was we introduced the notion of sinusoidal sources. So previously, all what we dealt with was DC sources. So now we have AC sources, and there are multiple options for AC sources. In this course and most of the power-related courses, you will be dealing with sinusoidal sources. A sinusoidal source can be characterized with the following equation. So it has a sinusoidal variation with respect to time, meaning that it could be cosine or sine. But in this course, and we're going to use the cosine convention. So in the cosine convention, you will have the amplitude, which is the maximum value that the source can achieve. You will have the angular frequency, the repetition of the cycles with respect to time, how fast the sinusoid repeats itself, and the phase angle. Here it controls the shift with respect to with respect to the origin. So if you recall from last time, we had this problem. So we're trying to find the current IL of t, and we had a situation where we have a source, sinusoidal source, and a switch. So at t equals to 0, the switch is closed. And we noticed that we did not derive this formula, but we will take it for granted here, that the voltage, or that the current consists of two parts. The first part is the transient, something that's going to appear temporarily, but it's going to die quickly. And we're going to have the steady state, something that's going to stay forever. For the steady state current, let's not focus on the transient because it's going to disappear very quickly, but let's focus on the steady state current. We notice here the steady state current has the same frequency as the voltage source. It has a sinusoidal nature. It has a sinusoidal nature with same frequency, but different phase and different amplitude. So the question is, can we find a way? Is there a way by which we can capture the changing parameters, meaning that we want to capture the amplitude and the phase, and ignoring the things that are fixed, meaning that we are ignoring the frequency? And the answer is yes. The technique or the way to do that is using Phasor Transform. So if you recall from last time, Phasor Transform is if you have a sinusoidal source, or if you have a sinusoidal signal or sinusoidal function, then the Phasor Transform of this one is simply the amplitude and the phase. So this transform captures the amplitude and the phase, things that are changing from one circuit to from one element to another in the circuit. If you have something in the phasor domain and you want to transfer it back to time domain, what you need to do is you need to apply the inverse Phasor transform. So you need to add e to the power j omega t and then take the real part, because here we are dealing with cosine function. If you are dealing with sine, then you probably need to do, or then you need to take the imaginary part. Okay, so if you remember last time, we solved several exercises on actually finding directly phasor form of a sinusoidal function and finding the time domain form of a sinusoidal source or sinusoidal voltage or current that's given in the phasor domain. We also noticed that we had a situation where we were trying to add two sinusoidal signals or sinusoidal functions. And these sinusoidal functions, we added them using two approaches. The first one is simply by manipulating simply by using trigonometric identity. And the second approach is by using, by transforming everything into phasor domain, then adding complex number, then bringing things back to time domain. Okay. So we studied phasor transform. We know about phasors, and the question is how to use phasor analysis in how to make use of phasor analysis. So how to solve the voltage and the current in any circuit if we have a sinusoidal source using phasor-based analysis or phasor-based techniques. So it turns out that we need to, first of all, we need to define something similar to Ohm's law. So you have a voltage, and this voltage is related by a quantity, is related to the current by the impedance Z. So in order to find impedance Z, we have three elements. We have the resistor, capacitor, and inductor. So let's find the relation between the current and the voltage in a resistor, and this relation is going to give us the impedance. So it turns out that the voltage or the current, we assume this is the current. Then by Ohm's law, the voltage is given by this formula. So which means that Z here is equal to R. So the impedance of a resistor is actually the resistance itself. The fact that we have a real impedance implies that the current and the voltage are in phase. If we have an inductor, however, then because of the differentiation here, we're going to have a purely imaginary impedance. And this impedance is given by J omega L. So from the fact that we have purely imaginary impedance, this implies that the current and the voltage are 90° out of phase. We plot them, we see that the voltage leads the current, or the current lags the voltage. And this shift, this 90° shift, corresponds to 1/4 of the period. So any questions about these concepts? Okay. So the only missing part here is actually to find the impedance of the capacitor. So if we have a capacitor, so what will be the impedance of that capacitor? So let's assume that we have the voltage of across the capacitor. So let's find the current. So we know that the current is C dV by dt. And V here is Vm cosine omega t plus theta V. So if we differentiate it, we'll get minus C Vm omega sine omega t. So if we transform everything, since we're using cosine convention, so let's write it in terms of cosine. So in this case, we'll have now if we apply Phasor Transform to this one, we end up with for cosine we have and we know from last time that this one is actually minus j. So we'll have j omega c Vm but what is Vm e to the power j theta v? This is exactly the voltage, the phasor form of the voltage. So the impedance is actually 1 over j omega c, or if I bring j to the numerator, it's going to be negative j omega c. So the voltage here is going to be Im okay. Any questions, Shabab? Remember, the impedance is and here we have the opposite. I equals to j omega cv. Okay, is it clear? طيب. So conclude that the impedance of the capacitor is 1 over j omega c, or if we move j to the numerator, is going to be negative j omega c. So this again, since we have purely imaginary impedance, this implies that the current and the voltage are 90 degrees out of phase. However, in this case, the voltage actually, or the current is actually leading the voltage, not the other way around. If you remember, for the case of inductor, the voltage leads the current, not the current leads the voltage. And this shift gives us it's a 90-degree phase shift, so it corresponds to 1/4 of the period. Ahmed?
دكتور الحين جاي رقيتها فوق.
Yes.
طيب هو المفترض تكون to the power minus 1 ولا
كيف to the power minus 1؟
يعني هي صعدت فوق.
Yes.
صارت to the power minus ولا أنا غلطان؟ شكرا.
Any other question? Okay. Very good. Let's summarize what we have. So first of all, we notice that the impedance is a complex quantity, but it's not phasor. So pay attention to this point. Impedance is a complex quantity. It's just like a step. If you remember last time, we said we need two things. So the first one is we need to have a complex representation or phasor-based representation or frequency domain representation of the circuit elements. And this is done through the definition of through the introduction of impedance. Also, we need to define the phasor form of KVL and KCL, and we'll come to it in a few moments. So the impedance is a complex quantity, not a phasor. This is very important. The imaginary part of the impedance is called the reactance. So for the circuit, for the three circuit elements that we studied, for the resistor, the impedance is purely real. So the reactance is not defined as zero, actually. For the inductor, the impedance is purely imaginary. So the reactance is omega L. And for the capacitor, is again, the impedance is purely imaginary impedance. And the reactance is minus 1 over omega C. So if you recall for DC analysis, what happens to the inductor? How does the inductor behave in DC, at DC? Ibrahim?
To behave as a short circuit.
Exactly, it behaves as a short circuit. So by looking into the definition of the impedance, so as omega approaches zero, which means we are approaching DC, the inductor behaves as a short circuit. It's very interesting to note here that as omega actually approaches infinity, as we increase the frequency, the inductor behaves like an open circuit. This is very important. You see this when you take EE to 13 and you are asked to design a filter. So a filter is a circuit element, or is a circuit that actually passes or allows certain frequencies to pass and stops certain frequencies from passing. You see that the variation of the behavior, the variation of the impedance with respect to frequency is very crucial in the design of these filters. Similarly, here if we have a capacitor, so as omega approaches zero, means this one is close to DC, the capacitor will behave like an open circuit because you'll have -1 divided by 1 over almost 0 multiplied by C, so this the impedance will be infinite. However, if you keep increasing the frequency, so as the frequency increases, the impedance of the impedance of the capacitor will be a short circuit, or the capacitor will behave like a short circuit. So what's true about the behavior of the capacitor and inductor at very low frequency is not true for, it's not the same as their behavior at very high frequencies. And this is very important, like you said, when you design a filter. Okay. So let me just give you a quick question. Okay. We can't hear you, okay. ما أسمعك. We can't hear you. طيب.
Can you hear me now, Doctor?
Yes.
Yes, Doctor. I did not understand why is there a difference between high frequency and low frequency.
Okay. Do you get why the impedance depends on the frequency, right?
Yes.
Okay. So what happens if you have an impedance of 0 ohm? So by the way, the unit of the impedance is ohm. So what's the what happens if you have an impedance of 0?
Short circuit?
Yes. What happens if you have an impedance of infinity?
Open circuit?
So if you take, for example, the inductor, you start from 0 frequency. Then it's going to be short circuit, and you keep increasing the frequency. the inductor will behave like an open circuit as you keep increasing the frequency.
Okay.
So think about it this way. Let's take an example here. If you have the following circuit, this is a voltage source. This is a resistor. This is an inductor. So your output is actually the voltage across the inductor. And you plot it with respect to frequency. You see that at very low frequency, what's the voltage across the inductor? Rahim?
It is 0.
Yes, it will be almost like this. So it will be 0, then it will keep increasing with the frequency until like some certain points at frequency, you see that. So this is the output. The output equals to Vs. So you see that at the very low frequency components are attenuated. The very high frequency components are passed as they are. So this one looks like a high pass filter. So it passes high frequency components and suppresses low frequency components. And we use the fact that the impedance of the inductor changes with respect to frequency. Let's take another example here. Let's assume we have the following circuit. So if I plot this one with respect to a frequency, so at very low frequency, the capacitor will behave like an open circuit. So the voltage across the capacitor will be the same as the voltage source. Then it will start decreasing until at very high frequency, this one will reach 0. So this circuit will pass only low frequency components and will suppress high frequency components. And this is a circuit element this is a circuit we call low pass filter. So it passes low frequency components. And again, we use the fact that the impedance of the inductor and the capacitor changes with respect to frequency. Is it clear to that?
Yes.
Okay. So now let's take this exercise. So in this exercise, we're asked to find the current. We're given the current in the inductor. And we're asked to calculate the inductive reactance. So what is the reactance of the inductor? Okay. So the reactance, let me call it XL. Yasser?
Yes, we can apply the formula. It will be omega by L. So
Yes.
30 times 10,000.
So exactly. So 1 to the power 4. And this one is 200 ohm. Okay, so Ziad, what is the inductor impedance?
We add the imaginary J.
Yes. Okay. So what is the phasor voltage, Walid? Walid. You're muted.
Yes, 10 cosine 30.
So this is the phasor what?
Sorry, 10 angle of 30, I think.
This one?
Yes.
This is the current.
Okay, the phasor voltage, right?
Yes.
I think it's ZI, impedance multiplied by I.
Okay, exactly. So the impedance is 200, 10 to the power 30, 10 and the angle is 30. So what is the polar form of J200? Fine. What is the polar form of J200?
It is e to the power.
So this is the polar form of J200. If it's minus J200, then the angle will be negative 90. Okay. So if I multiply them, I will end up with 2. Okay. So this is the phasor voltage. So what is the expression for the steady state voltage? Yes, sir.
Yes, it will be 2 cosine 10,000 t plus 120 degree.
Exactly. So you see that this exercise is very straightforward. All what we need to do is once we transfer everything into, once we write the frequency domain representation of the inductance of the inductor, we can actually solve problems in a way similar to what we did in chapter 4, chapter 1, 2, 3, and 4. Okay, so I wasn't planning on doing this, but since we briefly talked about it, so if you have say like 20J, then this is in rectangular form. So the polar form here, you don't need to do a conversion using your calculator. So it's going to be simply 20. The angle is 90. I think it stops. Okay, So when you have 20J, the angle is going to be, the polar form of this one is 2090. If you have minus 20J, then the polar form is going to be minus 90. If you have, say, 20, then the polar form of this one is going to be 20. The angle is 0. If you have negative 20, then the polar form of this one is going to be 20, negative 180. Okay? It's very important. So you don't need to do, you don't need to use your calculator. Okay, the last thing that we need before actually solving circuits using phasor domain analysis is to define KVL and KCL in the frequency domain. So you see that all what we need to do, so what we studied in chapter 3, or 2, I'm sorry, 2, both KVL and KCL is going to hold, provided that everything now is in complex domain. So we need to actually, first of all, we need to construct the frequency domain model of the circuit, meaning that if we have an inductor, we need to find the impedance of the inductor, we need to find the impedance of the capacitor, we need to find the impedance of the resistor, and we construct the circuit using this model. And we need to, I mean, this addition is, or these two equations are complex equations. So meaning that they are actually written in a complex number format. Any question? You see that studying chapter 9 is not going to, I mean, they're not much of a new concept. Everything we have in chapter 9 is something that we cover. The only difference here is we're dealing with complex number, not something new anymore. Okay. So now let's study one of the theories, or two of the theories that we studied in chapter 4. If you recall, we studied source transformation and Thevenin and Norton equivalent circuits. So now we are armed with the frequency domain representation of the circuits. We know how to manipulate complex numbers. So we can actually use source transformation. We can apply source transformation, meaning that if we have a voltage source in series with an impedance, then this voltage source can be transformed into a current source in parallel with an impedance. The relation between the currents and the voltage is exactly the same as in the case of DC circuits. The only difference here is we need to, the currents and the voltage are complex numbers. We can also define, or we can also write Thevenin and Norton equivalent circuits, and we will explain this in the following exercise. So let's start with this exercise. Let's assume that we are asked to find the voltage V naught here in the following circuits. And we are told to use source transformation. So what we need to do, we need to simplify the whole calculation to a voltage source in series with a bunch of resistors. So in order to do that, what you can do is actually you can take the two approaches. You can first redraw the circuit in the following form. So 1 plus J3, you can write it as Z1, impedance 1. Nine plus 9 minus J3 is impedance 2. Impedance 3 is going to be 0.2 plus J0.6. And impedance 4 is going to be 10 minus J90. And remember, you're asked to find B naught here, the voltage across impedance 4. So if you apply source transformation, the first step you need to do is you need to convert the voltage source into a current source. And this can be done by dividing the voltage V by the impedance Z1. So you'll have Z1 in parallel with Z2. Okay, so now you combine Z1 with Z2. So you combine the overall combination of Z1 and Z2. Then from chapter 4, you know that you will have a current source in parallel with an impedance, in parallel with a resistor in chapter 4, but in this case in parallel with impedance. So you can also convert it back to a voltage source in series with the resistor. So if you do this conversion without deep diving into details, you will have Z1 in parallel with Z2. The voltage is going to be V divided by Z1 multiplied by Z1 in parallel with Z2, Z3, and Z4. So now the finding the impedance or finding the voltage is straightforward. So it's going to be by applying the voltage divider law. In parallel with or multiplied by V1, so V divided by Z1 multiplied by Z1. Okay. So you find the impedance, or you're given everything in terms of impedance. You manipulate the complex numbers in this equation, and then finally substitute. So this is the first approach. The second approach is you do it step by step. So what we did here, we assumed that we have building blocks, and then at the end of the day, we're going to substitute. But you can actually start substituting from the beginning, meaning that if you apply source transformation to convert this circuit to a current source in parallel with the resistor, then you will have, so this is 1, this is 2. So the current is going to be the voltage divided by the impedance. So the impedance is 1 plus J3. The series impedance is 1 plus J3. So the voltage, I don't know why I keep calling it V1. Is going to be 4 minus J12. So if you redraw the circuit, you get 4 minus J12. So now we can do the same. What we can do now is we can actually combine these in parallel. We'll end up with the following circuit. We have Z1 parallel with Z2, which is 1 plus J3 parallel with 9 minus J3. Again, you can do all of these calculations in your calculators. 0.8 minus J 2.4 or plus 2. 2.4. So what was the current? 4 minus J12. So the real part of the impedance is actually a resistor. And if the impedance is positive, if the imaginary part is positive, it means it's an inductor. If it's negative, it means it's a capacitor. So now we need to convert it back to voltage source in series with an impedance. So in this case, we multiply 4 minus J12 by the impedance, which is 1.8 plus J2.4. So if you multiply it, you will end up with 4 minus J12 multiplied by 1.8 plus J2.4. And you will end up with 36 minus J12. Okay, so if you do that, so now it becomes straightforward. So you can apply voltage divider law, and it's going to be divided by 1 plus 8 plus J2.4 plus 0.2 plus J.6 plus 10 plus or negative J19 multiplied by the voltage, which is 36 minus J12. If you solve for it, you will get 36.12 minus J 18.84 volts. Okay, any questions about? Okay. Okay, we see that it's not that complicated. All what we did was just like dealing with complex numbers. So if we know how to deal with complex numbers, then we are not actually learning anything new. So let's have an exercise. Let's open. Yes, Ibrahim.
Doctor, before you said if the complex number was negative, it's capacitor.
Yes.
Okay.
Because there is no way for, first of all, we don't have negative frequency. We don't have negative inductance. So the only way you have a complex number, you have a negative complex number, is if you have a capacitor, since the impedance of the capacitor is minus J divided by omega C. Okay. So let's try to solve this exercise. In this exercise, we're trying to find the Thevenin equivalent circuit with respect to terminals A and B. This is terminal A, this is terminal B, and this is the Thevenin voltage. So we want to find the Thevenin equivalent circuit. So we need to find the V Thevenin and we need to find Z Thevenin. So let's just start with V Thevenin. Okay, if we want to start with the Thevenin voltage, so first of all, we need to apply the source transformation here. So we have a voltage source in series with a resistor. First of all, you don't actually need to apply source transformation. So you can actually use node voltage method. But dealing with complex numbers is not that straightforward. So I'm trying to minimize the number of equations that I need to invent.
Doctor, what about the voltage divider method?
You can do that with voltage divider method. No, you cannot. Since you have a source here, you don't have a resistor on the impedance here. Okay, so let's start with source transformation. So let's convert this one to a current source in parallel with a resistor, and then we'll convert it to a voltage source in series with the resistor. So what I will do is I will apply source transformation. So I have 120 and 12, so it's going to be 10. Luckily, the angle is 0. So it's going to be 12. And you will have 60. Put it down a little bit. VX. So Vx is actually the voltage across the 60 ohm resistor. So if I combine the 60 and 12, they are parallel. So the voltage across them will be still Vx. So that's what I'm going to do. I'm going to combine them in parallel. So 12 parallel with 60, this is going to give me 10. And if I combine them in parallel, I can also apply the source transformation. So if I apply the source transformation, remember from the property of the source transformation, so if this is point, say like A prime, this is B prime, then if you apply the source transformation, you should get the same voltage and the same current as well between the terminals. So the source transformation should not change the voltage. So this is still Vx. So if you apply source transformation, you will get 10 in parallel with current source. So this is going to give you 100. This is Vx. Okay. So let's see what I have in here. If I'm assuming that this is the current I that originates from the source, then this current will travel in this direction and it will circulate here. So meaning that the Thevenin voltage is going to be 10 Vx plus 120 multiplied by I from KVL. So what I need to do is I need to find Vx and I. So in order to find Vx and I need to actually find two independent equations. So the first one I can apply KVL in the big loop here. So if I apply KVL, I will get 100, 10 multiplied by I, minus J40 multiplied by I, plus 120 multiplied by I, plus 10 Vx. So if I simplify it, I will end up with 130 minus J40 I plus 10 Vx. So this is the first equation. The second equation is by applying KVL in this part. So Vx is going to be 100 minus 10I. So if I write it in the standard form, I will get 10I plus Vx equals 200. So this is the second equation. So I have two equations, two unknowns. I can easily solve for that. And inshallah, next lecture, I'm going to show you a method to actually solve such a system. Since most calculators do not allow you to solve a system with complex numbers. So if you solve for the system, you get I equals to 10.8 minus J 14.4 amperes. The X is going to be 208 plus J 144. The unit is volt. Then substitute into equation A. I call this one A. You will get Vthn equals to 784 minus J 288 volts. Okay, now we found the Thevenin voltage. Any questions, Shabab? Okay, the first step is done. So we found the Thevenin voltage. So let's find the Thevenin resistance. So in order to find the Thevenin resistance, there are multiple approaches to do. So the first one is you can actually connect, because here we have a dependent source. So what you can do is you can connect A with B and find the short circuit current. And from that, you can take the ratio, and this should give you the ratio of the Thevenin voltage over the Norton or the short circuit current is going to give you the Thevenin impedance. That's one approach. The second one is actually by applying a test source, and this is the approach I'm going to use. So I'm going to apply a voltage test, and I'm going to measure the, I'm going to find the current, the test current, and I take the ratio of the voltage test over the current test, and this should give me the required impedance. So let me do that. So if I do that, the first step I need to do is I need to deactivate all independent sources. So I have one independent source, which is 120. So I deactivate it since it's a voltage source. So it will behave like a short circuit. And I'm going to apply a test voltage source. Okay, in this case, what I need to do is actually, so let me further simplify the circuit. So I'm going to combine these two in parallel. In a class, hold on a second. I'm going to combine these two in parallel. And if I combine these two in parallel, what I will end up with is the following circuit. So Vx is going to be this one. And I of t is going to be, so this is the test voltage. And this is I of t. So in order to find I of t, what I need to do is actually I need to apply KCL here. So if I call this one IA, this one IB. So what is IA by KCL? So using KCL, IT, the terminal voltage or the test current is going to be IA plus IB. So IA is what in this case? What is IA, Shalom? What is IA? Yes, sir?
We can apply KVL on the outer loop. So
You don't need to apply KVL. It's going to be simple Ohm's law, Del Karim.
yes,
Yeah, go ahead.
yeah, it will be VT over 10 minus J40.
Yes, exactly. So this is IA. So what is Vx? What is Vx, Shabab? What is Vx, Ibrahim?
It is IA times 10.
Yes, 10 IA. So Vx in this case is going to be 10 multiplied by AA. So if I multiply 10, is going to be Vt 1 minus J4. Okay. So what is IB? Ahmed?
Doctor, didn't I divide it to IA? I mean, the first one goes to 10 Vx, and the others goes straight.
What do you mean by?
I mean, why it's Vx equal 10 IA?
This is Vx.
Oh, yeah. Thanks.
The grape. What is IB?
Yes. Thanks.
10 Vx multiplied by 120 or divided.
No, IB is going to be, by Ohm's law, is Vt minus 10 Vx. Something similar to what we did when we apply non-voltage method.
Yes, clear.
It's going to be Vt minus 10 Vx. So IB is going to be Vt over 120, 1 minus 10, 1 minus J4. So if I solve for it, I end up with here we have to solve some problems in this one because you need to be familiar with complex numbers and familiar with how you use calculator to solve complex numbers. So this one is equivalent to 12, 10 minus J40, and So IT will be IA plus IB. So it's going to be VT 10 minus J40, 1 minus 9 plus J4 divided by 12. Okay, so I think I need more space here. So IT is going to be VT 3 minus J4 whole 10 minus J40, and this implies that the Thevenin resistance is going to be VT divided by IT, and in this case is going to be 91.2 minus J 38.4 ohm. Okay, so now we found the Thevenin resistance, we found the Thevenin impedance, we found the Thevenin voltage. So the Thevenin equivalent circuit is simply like this. So any question, Shabab? Ziad?
What could be the representation if the imaginary part was positive other than an inductor?
It has to be an inductor.
Okay.
If the imaginary part is negative, then it's capacitor. If the imaginary part is positive, then it's inductor. Any other question? Okay. Let's solve one more exercise before we conclude. And inshallah, tomorrow I will show you a method. Tomorrow, inshallah, we'll cover mesh and node voltage methods. And this most likely will be our last new topic. Actually, this is actually our last new topic. So after today's lecture, we're not going to introduce anything new. Basically, we're going to be familiar with how to deal with or how to solve complex numbers, how to solve solve AC circuits. Okay, so in this circuit, we're doing something different, actually. So we're asked to find the steady state expression for for V naught T, and we need to use the technique of the source transformation. You see that this is a very simple circuit because you have two sources, and these two sources are kind of like if you apply source transformation, then you will end up with two current sources in parallel, and you can combine them into one single source. But the difference between this problem and the problems that we solved before is that now everything is given in time domain. So we need to do one step further here. So we need to convert everything into frequency domain. Meaning that we need to start with the sources. For example, V1, we need to have the phasor form of V1. So what is the phasor form of V1? Rahim?
240, and the angle is 43.30.
Exactly. Walid, what about V2?
96, the angle is minus 90.
96 and the angle is minus 90. Exactly. because it's given in a sine form, so we need to convert it to cosine. Then we need to do the same with the impedances here. So the impedance of the resistor will stay as it is. The impedance of the capacitor and the inductor, we need to actually find them. And let's start with the impedance of the inductor. So ZL is going to be J omega L, and omega in this case is 4,000. L is 15 milli. And this is going to give us J60 ohm. For the capacitor, the impedance is minus J divided by omega C, and we're given that the impedance is 25 divided by 6. So this is going to give me okay. So now I need to apply source transformation here. So I have voltage source in series with an impedance here. So the impedance is J60. So in order to convert it to a current source, in parallel with J60, so I need to do the following. So the voltage is 240. The angle is 53.13. The impedance is J60, which means it's going to be 240, 53.13 degrees divided by 60. And this is going to give me 3.2 minus J 2.4 ampere. Similarly, for the second source is actually it's easier than the first one because this one is purely real. So the voltage is 96 and the angle is negative 90. So V2 divided by 20, 96 negative 90 divided by 20, and this is going to give minus J 4.8 amperes. So now I need to draw the circuit here. So the current source is going to be 3.2 minus J 2.4. I have J60. I have 30 ohm. I have negative J60. I have 20 ohm. And I have minus J 4.8. So now the voltage that I'm interested in is the voltage across the parallel combination. So what I need to do is I need to reduce the entire circuit into a current source in parallel with the resistor, with an impedance. So I need to find the equivalent impedance here. So the equivalent impedance here is 1/30 plus 1/J60 plus 1/20 minus 1/J60. So it turns out that the impedance is going to be actually real here. Which is good. I need to subtract the sources. So 3.2 minus J 2.4 minus 4.8. And this is going to give me 3.2 plus J2.4 12, and this is the phasor of V0. So V0 is going to be 12 multiplied by 2.2 plus J2.4. So it's going to be 38.4 plus J28.8, or 48 angles 36.87 degrees volt. Okay, remember here you're asked to find the steady state expression for V0. So you need to take the inverse Phasor transform here. So if you take the inverse Phasor transform, you get 48 cosine. The frequency should be the same as the frequency of the source, which is in this case of the sources, which is 4000 T. And the unit is volt. Any questions? Yes, sir.
Doctor, we did not apply here source transformation. Is it because we have the same frequencies in both sources?
We did apply source transformation.
We did apply. Where did we apply?
We started sources and we put everything into current sources.
We applied it at the beginning. Yeah.
Yes.
I did not notice.
Okay. Any other questions, Shabab? Okay. See you, inshallah.